So the third operator here, which is also qualifies as unary relational operator, is called rename, which is represented or denoted by rho, which is a symbol which you can see here, and it is pronounced as rho, RHO. In some cases, we may want to rename the attributes of a relation or the relation name or both. So, in various algebraic expressions, wherever we have more than one operators, so there we can use that row operator or a rename operator to rename the resultant relation, and that is helpful for us to understand that how actually these operators are applied. So useful when a query requires multiple operations, of course, necessary in some cases when we will discuss join as well. So in that case, sometimes it is very important to use rename rather than to express in a single statement. The general rename operation row can be expressed by any of the following form. So you can use row S, that is the name, and B1 to Bn, or changes both the relation name to S, that relation name will be changes to S, and the column attribute name B1 to B1. That is possible. So you have changed the column name. Actual column names might be the employee number, employee name, address, and let's assume you have changed it to B1, B2, B3, B4, Bn. And similarly, the relation is R, which is replaced by S. So you have given the new name. Normally, when we do this thing, when we have some intermediate relations, whenever we are using multiple operators. So the relation PSR changes the relation name only to S. So in the second example, only the relation name is changes, not the attributes. In the first example, the attribute names are also changed and the relation name is also changed. And in the third scenario, only the attribute names are changed, but the relation name is not changed. So there are three possibilities. Either you can change the name of, whenever I say change the name, it does not mean it's a permanent change. The change is only done on that particular query which has to be executed, or the expression which you are going to write down. So it is up to you. Either if you think that both the attribute and name and the relation name has to be changed, then you can also do with the row operator. If you only want to change the relation name, you can again use the row operator, and similarly it is also possible you might only change the attributes. So for convenience, we use a shorthand for renaming attributes in an intermediate relation. So here you can see that you applied pi, that is what? That is a project, and project is applied whenever we are interested in some of the attribute. Let's suppose f name, first name, last name, and salary, and that is the relation dep5 underscore emps, which is what is an intermediate relation, and which shows that here we are talking about employees who works in department number 5. That, and that arrow says that the value of this query will be go into this result, which is a rename now. So result will have the same attribute name as whatever the attributes in this relation. Or if we can write here, now the attribute names are changed. Here you change the attribute with F, M, L, S, B, A, S, X, S, A, L, S, U, D, N, O. So you can also change the attributes. So, but remember, whenever you change the name of attributes, one thing is very important, that you must have the same number of attributes in that relation. Let's suppose if in this relation you have 5 attributes, so then you have to have 5 rename attributes over here. You cannot then write 4 attributes or 3 attributes. Then it is, yes, it is something like alias, uh, and it has resemblance with alias, because we are just changing that name for a little purpose, not permanently, to use for an expression. So similarly, now we can see the representation here. We have seen the representation over here, and now you understand the concept that why that rename is used. And Now the next operator which we will going to discuss is called union. Now remember that union is a set theoretic operator. Union is considered to be a set theoretical operator, and and uh, the union, we talked about intersection, we talked about Cartesian product, difference, all these are set theoretic operations. So union is what? Is a binary operator, because whenever we apply union, if you recall your set theory, you remember that whenever we use union, it is applied between at least two sets. So we want to see the a set of natural number union with the set of prime numbers, and we have the result. Or you have the set of prime number union the set of odd numbers. So we always have union between two sets. Similarly here, union is actually a binary operator represented by the symbol U. The result of our union S is a relation. So whenever we apply union, the resultant is also a relation that includes, remember, all the tuples that are either in R or in S, or in both R and S. And in union, only the duplicated tuples are eliminated, and you count all the tuples. And if both the relations have same tuples, then it will be represented once. So there will be no duplicated tuples in the resultant relation. The two operand relations R and S must be type compatible. This point is very important for you people to understand. Otherwise, you will make problem, or you will confuse whenever you write an expression. So, whenever there is a term used over here, which is you can see as type compatible. Type compatible means that type compatible is only applied whenever you are using union, intersection, or difference. So all these three operators, whenever you apply between two relations, those have to be union compatible. To be union compatible, you have to see in both the relations. The first condition is what? That both the relation must have the same number of attributes. Let's suppose if you want to apply union between a relation R and a relation S, the first condition is the attribute must be same. The must be same in number. Let's suppose if in R we have 5 attributes, and let's suppose in S we have 4 attributes, there is no possibility that we can take a union. Just stop over here. We cannot take a union. So if there are 5 attributes in S, then 5 attributes in R. This is the first condition. Second condition, that each pair of corresponding attribute, for example, first attribute of R and first attribute of S is the corresponding attribute. Second attribute of R and second attribute of S are the corresponding attributes. So each pair of corresponding attribute must be type compatible, or in other words, you can say both can take the values from same domain. For example, I give you the example which is type compatible, and I will also give you one example which is not type compatible. For example, the second attribute of the relation R describes the joining date of an employee, and the second attribute of S is also define the joining attribute of an employee. So it means both takes values from the same domain, and it means they are type compatible. But let's assume the second attribute of the R is the last name, and the second attribute of S is the salary. Now, the salary takes values from entirely a different domains, which represents the currency value, which correspond to a specific position of an employee, and represents a specific number. Correspondingly, the last name is basically a textual value or a string value which represents a name. So there is no compatibility with union compatibility among these two attributes. So if this is the case, then union cannot be applied. So union can only be applied if they are union compatible. Same number of attributes and the corresponding attribute takes values from the same domain. Okay. So the example of union operator, to retrieve the social security number, normally we call it SSN, and in North America normally they have social security numbers of all employees who either work in department number 5 or directly supervise an employee who works in department number 5. No, now now you want to retrieve SSN value of an employee who either works in the department number 5, that is represented in result 1. You can see here DP5 underscore employees. So you have applied sigma DNO is equal to 5 to employee, and that values goes to result 1. So here in the result 1, what we have? We have what? We have the employees or directly supervise an employee who works in department number 5. So where we have another attribute in the employee table that is called super SSN, means an employee who is supervising that employee. So pi super SSN DP5 EMP5. What is the resultant? That is called result 2, which is also gives you the SSN. And what you want to do, because you need both the employees in that query, so what you can do, you can take the union. So you have you have retrieved the employees in two separate conditions, and then you take the union. So this will give you all those employees who either work in department number 5 or directly supervised by an employee who works in department number 5. So that is again an example of a union. So here you can see the result 1 gives you these 4 SSN, and result 2 gives you these 2 SSN. And in the resultant relation, you have 1, 2, 3, 4, and 5 SSN. Why? Because in the result 2 SSN, you can see the first value which is also there in the result 1. So this is the common value. The common value is always represented only once in the union operation. So here then the resultant relation you have what? You have 5 tuples. The type compatibility operands is required for the binary set operation union, also for intersection and the difference as well. So R1, let's assume there are attributes A1 to AN. R1 is a relation having attributes A1 to AN, and R2 as another relation having attributes B1 to BN are type compatible if they have the same number of attributes, and the domains refers to what is the range or the type of values an attribute can hold. That is called domain. The domain of corresponding attributes are type compatible. That is, domain of AI is equal to domain of BI. In other words, you can say domain of A1 is equal to domain of B1. Domain of A2 is equal to domain of B2. Domain of A3 is equal to domain of B3. The resulting relation from R1 union R2, also in the same case of intersection or difference, has the same attribute name as the first operand relation R1 by convention. So now we talk about intersection, and just recall again the knowledge from your set theory. Whenever we take the intersection among two sets, what is the resultant? Resultant is always the common element. So same operation applied when between the relations. What is the resultant? The resultant is the common tuple. So if you want to have an intersection between two relations, it means you are looking for only the tuples which are present in both the relations. That's it. So the result of operation R intersection S is the relation that includes all tuples that are in both R and S. The attribute names in the result will be the same as the attribute names in R. The two operand relation R and S must be type compatible. So of course that has to be type compatible, because we are talking about an intersection relation. And what is the set difference? Set difference is normally represented by minus. So if there is a relation R and there is a relation S, what is the result of R minus S? R minus S means all those tuples which are represented in S, and let's assume they are also represented in R. In the resultant, all those tuples will be actually will not be represented. So you can say that R minus S is a relation that includes all tuples that are in R but not in S. So the attribute names in the result will be the same as the attribute names in R. So that will remain the same. The two operand relation in R and us must be type compatible, because we have recalled this thing many times that type compatibility condition holds for union, intersection, and difference. Now we can see the examples as well. You can see here that you can apply this to various relations, and you can see the example. Let's assume you can see the relations in the A diagram. In the A diagram, you have a relation student and instructor. In the student relation, there are two attributes, fn and ln, and in the instructor relation, we have two attributes, fn, fname and lname. So the two relations are union compatible. So you can take the union. So let's assume that you can take the union, that is the resultant relation. So the common tuples are represented only once, and all tuples will be counted in the resultant relation. Similarly, if you want to see the C, that is student and intersection with instructor. So if you make the intersection, only two, Suzanne and Zhao. You can see Suzanne and Zhao is here. So Suzanne and Zhao are represented in intersection relation. Similarly, the Ramesh and Shah. Ramesh and Shah is represented here, and Ramesh and Shah is represented here as well. So that is represented in the intersection relation. And that is the minus or the difference relation. Student minus instructor. So any row which is represented in instructor should not be represented in the resultant relation. So you can see here that the Ramesh and Shaw is here, the Ramesh and Shaw is here. So in the resultant relation, you can see Ramesh and Shaw are not represented. Similarly, Suzanne and Jaw is not represented over here. And in the last relation, you have the instructor minus the student. Here you can see the instructor minus the student. Remember that the union and intersection, they are actually the follows the commutative property. But when we talk about the set difference that does not follow the commutative property. So it means that instructor minus student does not equal to the student minus instructor. So that you have to keep in mind whenever you apply these relational operators. So you can also combine those various operators to form a complex expression. As you can see right now, that let's assume we have more than two relations which are involved. Let's assume we have three relations. One is represented as R, the second one is as S, and third one as ST. So we might have the union between S and T, and then the resultant, you can take the union with R. And similarly, you have the other way out. It means that you can take the union with R and S and then union with T. And in the last point, you can see that that property does not hold for the difference operator. Now we talk about the Cartesian product. Cartesian product is a product or an operator which we normally knows whenever we apply between sets. What it does, it gives you all the possible combinations out of it. So when we apply between sets, what happens? Let's suppose a set consists of 5 elements and the other set consists of, let's suppose, 10 elements. So we have the combination of each element with the other element. So The resultant elements will be 5 multiplied by 10, that is 50. But when we apply the Cartesian product between relations or a cross product between relations, so relation involves tuples and attributes. So in the resultant relation, let's suppose in the relation R1, we have 5 tuples, and in the relation R2, we have 10 tuples. Then you multiply the cardinality. The cardinality is 5 in the R1 and the cardinality is 10 in the R2. So in the resultant relation, we have 50 tuples. And the degree will be added. What is a degree? Degree is the number of column in a relation. So let's assume that there are 3 columns in R1 and let's assume there are 5 columns in R2. So in the resultant relation, we have 8 columns and 50 rows. That is actually the Cartesian product, which is represented by cross. And the commutative property you can also define in terms of the Cartesian product, because it gives you all possible combinations, and you can apply Cartesian product among various relations. So here you can see that cross product, you can also say it's not a very meaningful operation. Why? Because if you applied it without any proper means guidance or without understanding, it is not a meaningful operation. Why? Because it gives you all the possibilities, all possible combinations. So normally we are not interested in non-possible combinations. We are interested in combinations where we have specific values. For example, that you can see here that we are only interested in the first step, we are interested in only female employees. Then we are interested in only the first name, last name and SSN values of those female employees. And in the third step, you can see that employee names cross the dependents. So we want to have a cross product of all employees with their dependents. So the employee dependent will contain every combination of the EMP names and dependent, whether or not they are actually related. So whenever we have all possible combinations, so there we also have combinations which are not relevant, which are not important, but because all possibilities are being generated. So all those combinations are also found which are where we do not have any requirement. For example, the dependent is only related to employee 1, but when we have applied cross product, what is the disadvantage? That the employee 2 also have the combination with all those dependents. Employee 3 also have the combination with those dependents. That is why the cross product has to be applied very carefully. Otherwise, it will create problems. It will generate more work. And obviously, it is not recommended to use directly the cross product. Here you can see the results of the female employees and the employee names, and you can see the cross products of employees and dependents. Here you can see all combinations coming up, all combinations of the employee with their dependents. So some are okay, but the others are generated without any meaning. So that is why normally we avoid this. For that purpose, we use join operator. Join is more valid operator, or you can say a precise operator, where we have information which is involved out of two or more relations. And join operator is the symbol of the join operator is this one. You can see over here like a bow. So its join operator is like a bow. You can see here the sequence of Cartesian product followed by a select is used quite commonly to identify and select related tuples from two relations. So if you have a Cartesian product, you want to apply the Cartesian product, then you apply the select first, because what does select do? It reduces the tuple. So if it reduces the tuple, then the resultant is, of course, in the resultant relation, we have less tuples. But if without any restriction, we apply the Cartesian product, then it will give you the all possible combination. So that thing is actually done with the help of join operator, which combines the sequence into a single operation. This operation is very important for any relational database with more than a single relation. Join is always applied whenever you have more than one relation, because it allows us to combine related tuples from various related relations. Let's suppose if we have a relation R, A1 to AN are the attributes, and we have the relation as B1 to B1 are the attributes. So you can have a join with R and S. You can see the join symbol, and here is the condition where R and S can be any relation. For example, you want to have join with employee and department relation. So you can join these two relations. So where R and S can be on any relation that results from general relational algebraic expressions. So you can see over here that suppose we want to retrieve the name of the manager of each department. To get the manager name, we need to combine both the department tuple and the employee tuple whose SSN value matches the MGR SSN value in the department tuple. We do this by what? With the join operator. So what we do in the first step, we apply the department join MGR SSN is equal to SSN. So we equate two SSN which are there in department and employee table. So here we use equal to. So whenever we use equal to in the join condition, we call it equi-join. What we call it? We call it equi-join. So here we can get the department manager. And MGR SSN is equal to SSN is what is a binding condition and also called a join condition. So which combines the record from department to the employee and which sees that where those values are equal. So wherever those two values are equal, that department manager name will be appear. The join condition can also be specified as department.mgrssn is equal to employee.ssn. You can also write in that manner as well. Here you can see the department manager when you applied the join between the department and the employee with respect to the SSN, these three records turned out. So some properties of join. So you may have join between more than two relations, and you can see the various conditions you might apply. So the resultant, if you want to have all the attributes, then in the resulting attribute, the degree will be added. So let's suppose the degree is here n and degree is here m. So n plus m attributes will come. And all those resultant tuple must follow that condition. So that is the properties of the join. And that join condition is also called a theta condition, so on and so forth. So with this, I conclude over here the concept of join with this slide. That is the concept of equi-join. Equi-join is a join where you have a common attribute in both the relations which you want to join, and you actually join with the condition that wherever those two values equate. So with this, I conclude over here the concept of relational algebra, and I hope that you have understand the concept. Thank you so much.